Hello, so this video is going to be over topic 1.6 and 1.7, determining limits using algebraic manipulation and also selecting different algebraic procedures to determine those limits. So this video is a little long. It goes through a lot of different algebraic methods for you to use, and feel free to pause anytime that you need, and you can work through problems before I get to them. Okay, so the first method that we're going to talk about is direct substitution. And when you have continuous functions, direct substitution is the easiest way to go about it. So I'm going to do everything algebraic. There's graphs located within the notes to kind of help you support your answers, but I'm going to kind of do everything analytical, show you mathematically how we can calculate the limit using these values. So for example 1, I give you the function x squared minus 2x plus 1. So that's the quadratic. And what I'm going to do is I'm going to, excuse me there, I'm going to substitute. I'm going to do a direct substitution into this limit. So what I'm going to ultimately get is I'm going to get a negative 1 squared minus 2 times negative 1 plus 1. Okay, and if I evaluate that, I get a 1 plus 2 plus 1, which gives me an answer of 4. Now, we can support our answer here because at negative 1, if you look, it's a two-sided limit from the left and from the right-hand side, you're going to a y value of 4. Right, so we can always check ourselves with the graph. Now, if I do the same thing at 1, I'm going to kind of just switch colors here. I can now have a 1 squared minus 2 times 1 plus 1. And if you evaluate that, I get 1 minus 2 plus 1. And if we combine all those like terms, we get an answer of 0. And again, at 1, if you check from the left and the right, because it is a two-sided limit, you will get the value of 0. Okay, so direct substitution. If it's continuous, we can just substitute in. The textbook and AP kind of distinguishes three different types of functions, which you should be aware of. If you take the limit of a constant function, so it's just a horizontal line, no matter what x value that you use, you're always going to just be given the output of that constant function. So that's kind of nice. If you have a function that is continuous, we can, and what we did already, you can substitute in c for that input value, and then you'll just end up be getting f of c, whatever that is. And then last but not least, if you have x to a power, all of those power functions, linears, quadratics, cubics, quartics, they're all continuous. So it's kind of like 2 and 3 are the same thing. Ultimately, you're just going to end up getting c substituted into that function. And we would end up just getting c to the n power. Okay, so let's take a look just at a couple examples of those, just so you can see them. If I take the limit of the function 5, now 5 is a constant, so it really doesn't matter what x value I choose. For any x value, that limit will just be 5, okay, because all the outputs are 5. If I have for part B, as x approaches 2, well, this is a quadratic. Quadratics are continuous, so I can just substitute in, and I'm going to get 4 times 2 squared plus 3, which gives me 4 times 4 plus 3, or in this case, 16 plus 3 is 19. Okay, and I get 19 as my answer. For the next, if I find the limit as x approaches 1, now what I want to do here is if I do a direct substitution, I like to, for quotients especially, I'm going to separate this limit. So the limit as x approaches 1, x squared plus x plus 4. With quotients, we tend to get into some problems. So I just like to build good habits using those properties we discussed in an earlier section. You can separate this quotient into the numerator and denominator. If I then substitute 1 in, I am going to get let's see what we get here. If I plug 1 in, I get 1 squared plus, excuse my stylist here, plus 1 plus 4 all over 1 plus 1. So that gives me 6 over 2, or in this case, 3. Okay? And then last but not least, the sine function is continuous. So we can substitute that sine function in. I get the sine of pi over 2. And if you think about your unit circle for a second, again, this would be a no calculator question. Sine of pi over 2, you're expected to know that that would just give you an output of 1. All right, so these are all continuous functions. We can just do a direct substitution, plug in, see what we get, right? So same idea here. So I have a rational function, and I want to see what these limits are going to give me. So if I set this up, I'm going to have the limit of x squared minus x minus 6 all over the limit of x minus 3. If I plug in a negative 1 into this, I am going to end up getting a negative 1 squared minus a negative 1 minus 6 all over a negative 1 minus 3, which gives me, what is that? 1 plus 1 is 2, so that's going to be a negative 4 all over a negative 4. So that output is just going to be 1. So let's use our graph to check our answer here, because I gave you the graph of that function. As I approach negative 1, and it's a two-sided limit, so from the left and from the right, I am going to that value. I get an output of 1. So let's try g of x. Let's try at 3. So if I do this, I'm going to do it the same way. The limit as x approaches 3 of x squared minus x minus 6 all over the limit as x approaches 3 of x minus 3. And if I do this, if I plug in that 3, I get a 3 squared minus 3 minus 6 all over a 3 minus 3. Excuse, there's my minus, which gives me there we go, 0 over 0. Now, 0 over 0 is kind of an interesting fraction because you get some rules that kind of contradict each other, right? You've always heard if 0 is in the numerator, my fraction is equal to 0. If 0 is in the denominator, it's undefined. If you have the same thing in the top and the bottom, it's supposed to be 1, right? So we have all these algebra rules that kind of contradict each other when we have 0 over 0. So this is what we call indeterminate. Okay. And what we have to kind of go about some things very specifically when it's indeterminate. If you read through this, when it's indeterminate is ultimately we have the opportunity where you might have a hole or a jump or some sort of discontinuity, letting you know we need to kind of simplify that function a little bit more. So what we need to do is we're going to kind of examine those. What happens when we get those indeterminate forms and what they're going to turn out to be. So if you take a look at example 4, we're going to, this section is going to really be factor and cancel, right? What's going to happen if we factor and cancel this down into a simpler form of the function. So for part A, it says, note that there are two x values for which the function does not exist. Using the function f of x above, evaluate each limit using direct substitution. Does either of them yield an indeterminate form? So let's start at 2, right? So if I plug in 2, I'm going to get a 2 squared minus 4 times 2 plus 3 all over a 2 squared minus 5 times 2 plus 6. So let's see what this gives us. If I do 2 squared is 4, 4 minus 8 is negative 4. Negative 4 plus 3 is a negative 1. All over 2 squared is 4. Minus 10 is negative 6 plus 6 is 0. Now, this is not an indeterminate form. This is just straight up undefined, right? So this limit does not exist. Now, you can see from the graph as I approach 2, right, because that's the one we're doing, from the left and from the right, those two are clearly going to different values. And not only that, they're going to infinities. In order for our limit to exist, we want it to go to like a discrete value. In this case, it goes to infinity. So we want to take a look at the next one here. If I plug 3 in, I'm going to get 3 squared minus 4 times 3 plus 3 all over 3 squared minus 5 times 3 plus 6. And if I check that, that's going to end up giving me 9 minus 12 plus 3 all over 9 minus 15 plus 6, which gives me 0 over 0, right? So that is indeterminate. So this one, okay, is the one that's indeterminate. And that's the one that we're going to take a closer look at, right? So using proper notation, right, we're going to show why algebraic manipulation is necessary. So here's what I'm looking for. Whenever you want to, before you simplify a function, you have to show this indeterminate form, but we have to do it in a very specific way. So using proper notation, you have to split this up. So the limit as x approaches 3 of the numerator, x squared minus 4x plus 3 all over, and you have to make that limit on the bottom, as x approaches 3 of x squared minus 5x plus 6. If I then evaluate this limit, this is 0, and this is 0, okay? That is the proper notation. We have to show that first before we do anything else, okay? So then the next part is what algebraic manipulation can be done, right? And this is where the factoring and canceling comes in. So ultimately, what I want to do is I want to factor this numerator. I'm going to say, okay, I have an x minus 3. I have an x minus 1 all over. If I factor the denominator, that's an x minus 3, x minus 2. Okay, now the x minus 3's cancel. Now I'm very careful here. I don't use an equal sign because after I cancel it, they're not really going to be equal. I'm going to call the numerator an x minus 1, the denominator an x minus 2. This is what we call the extended function. Oop, help if I could spell. Let's try that again. There we go. Okay. So this is what we call the extended function here. And this function we can use. The original problem and the extended function will have the same limit values. Okay? Ultimately, we're just removing the holes. So using this, we know that this limit, this original problem, will be the same as the limit as x approaches 3 of x minus 1 over x minus 2. And if I now do a direct substitution with 3, I get 3 minus 1 all over 3 minus 2, and I get 2 over 1, which is just 2. Okay? So again, factor and cancel. Show why it's indeterminate using proper notation. Write your extended function. Use your extended function to evaluate your limit. That's going to be the theme for the day today. Okay? So example, I have 3 more examples. I'm going to put them up on the screen. Feel free at this point to pause. Okay? You can work through these the same way. And what I'm going to do is I'm going to work through, and then you can kind of check your answers. If you don't want to pause and you just want to listen to me work through, by all means, please do. But I'm going to work through all 3 of these. So I'm going to start by checking if they're indeterminate. So I am going to do the limit. Get my stylus working here. There we go. So I'm going to have the limit of x squared minus 25 all over the limit. Oh, you know what I forgot? Excuse me. I forgot to put what x is approaching, right? So shame on me. Let's try that again. The limit as x approaches -5 over the limit as x approaches -5. And the bottom is an x squared plus 2x minus 15. I can write here. There we go. And if I then plug in -5, that's going to give me 0 for the numerator. And if I plug in -5, I get 25 minus 10 minus 15. That also gives me 0, so it's going to be indeterminate. Never make an assumption there. Always check. Okay? So now what we want to do is we want to write the extended function. So the limit, okay, so the original limit as x approaches -5 of x squared minus 25 over x squared plus 2x minus 15 will be equal to the limit as x approaches -5. So you can see my flow of work here. That's important. X plus 5, x minus 5, all over x plus 5, x minus 3. There we go. And the x plus 5's cancel. So that limit will still be equal to, as x approaches -5, of x minus 5 over x minus 3. And now I can do a direct substitution, which gives me a -10 over a -8, or in this case, it gives me 5/4. Okay. Part B, same idea. Check the indeterminate form first. So the limit as z approaches 8. I know I caught you guys off guard with that z. Of 2z squared minus 17z plus 8 all over the limit as z approaches 8 of 8 minus z. If I plug in 8, I get 16, so, I'm sorry, 64, 128. I'm pretty sure I worked this out before. That does give me 0, and this does give me 0. So now I'm going to factor, okay? So I'm going to write my extended function. So as z, oh, I wrote an x. Shame on me. We're working with z's here. Z, as z approaches 8, of 2z minus 17z plus 8 all over 8 minus z. I'm going to factor, so the limit as z approaches 8 of, let's see, practice your factoring skills here. This is going to be a minus 8 and a minus 1, all over 8 minus z. Now, the numerator and denominator have almost the same factors. The only issue here is that when you cancel this out and cancel this out, you're going to be left with a -1 on the denominator. Okay, so they're almost the same. Just one is the opposite of the other. So I'm going to get a -1 there. So that gives me then the limit as z approaches 8 of 2z minus 1 all over -1. And if I plug 8 into there, I get 16 minus 1 is 15. 15 over a -1 gives me a -15. So this would be my answer. Okay, let's keep going. All right, so the limit as h approaches 0, right? So if I do this, let's check the numerator and denominator. So I have the limit as h approaches 0 of 6 plus h squared minus 36 all over. Limit as h approaches 0 of just h. If I plug 0 in for h, I'm going to get 36 minus 36 on the top, which is 0. And the bottom would, of course, be 0. So now I am going to go ahead and try to reduce this. So the limit as h approaches 0 of 6 plus h squared minus 36 all over h. Now, the only way that I can really go about this is to distribute out the top. So I'm going to say I have a 6 plus h minus 36 all over h. Now, if you distribute out this numerator, I get 36 plus 12h plus h squared minus 36 all over h. So do all your double distribution, right? Wonderful things happen. Cancels, right? So now I have the limit as h approaches 0 of a 12h plus h squared all over h. Now I can factor and cancel. Plus h all over h. The h's cancel. So now I have the limit as h approaches 0 of 12 plus h. And if h goes to 0, I'm just left with the 12. And you should be proud of yourself. There is my solution. Okay. So let's take a look at a second type of problem. Okay. I'm going to simplify complex rational functions, right? I'm going to go through, and ultimately the name of the game here is common denominators. So I'm going to use proper limit notation. So I'm going to say the limit as x approaches -3 of 1 over x plus 1 over 3 all over the limit as x approaches -3 of x plus 3. And if you plug a -3 into here, I get 0 over 0. So we need to talk about the algebraic properties that we can use to rewrite this in a different way, right? So I'm just what's called a complex fraction. I'm going to get common denominators, and then I'm going to try to simplify it up. So, whoa, got a little jump there. Sorry about that, guys. So if I do this, I'm going to multiply this first fraction by a 3 and this second fraction by an x. And that's going to give me now a 3 over 3x plus 1, I'm sorry, x over 3x. And that's all over an x plus 3. Now, it does help me if the denominator is also a fraction. You'll see why here in a minute. But now that I have common denominators in the numerator, I can say I have a 3 plus x all over 3x. And then on the bottom, I have an x plus 3 over 1. So I have a fraction over a fraction. The best way to reduce that is to multiply by the reciprocal. So I have a 3 plus x all over 3x times a 1 over x plus 3. Now, 3 plus x and x plus 3 are the same thing. Addition is commutative. So what I get here is I get a 1 over 3x as my extended function. I probably shouldn't use an equal sign. After you cancel things out, it's not really equal, but it's going to have the same limit. So if I use that extended function, I know that the limit as x approaches -3 of a 1 over 3x will just be a 1 over, excuse me here, a -9. And that's my answer. Okay. Now there are 3 more problems, and actually there's only really 2 because we can cross off that second one. There are 3 more problems for you to do. Just for the sake of my video not being terribly long, because we have a lot to do today, I am going to put up the answers that I got, and you can kind of check. So the answer that I got was a -4, and the answer that I got for part B, if you do it all right, believe it or not, I get part B. If I can write on my screen, come on, pen. Here we go. This does not exist. Okay, so if you do these 2 problems, you should get those 2 answers. Again, if you have questions, we'll talk about it in class, but for right now, see if you can get those. All right? All right. Next style. If I have a rational function, but I have radicals, I want to use conjugates, right? So how do I simplify something with a conjugate? So we're going to go the same way. I want to show you that it's indeterminate, and I want to show you how to reduce it into that extended function, and we can kind of go from there. So for part A, if I were to take, and I take the limit as x approaches 4 of square root of x minus 2 all over the limit as x approaches 4 of x minus 4. If I substitute 4 into the top, square root of 4 is 2 minus 2. That's going to give me 0. And if I plug 4 in the bottom, that, of course, gives me 0. So you can see that indeterminate form. So now here's how conjugates work. I'm going to use the same terms but the opposite operation, right? So I'm going to use the same terms on top, but I'm going to do the square root of x plus 2. Now, the rule of math, it's a golden, you've heard it a million times. What I do to the numerator, I'm going to do to the denominator. So I have the square root of x plus 2 in the denominator as well. Now, if you distribute this, the square root of x times the square root of x is just x. Square root of x times 2 is 2 square roots of x. Keep going, I get a minus 2 square roots of x, and -2 times positive 2 is a -4. And those middle terms cancel. Now you could probably look ahead at what I have here. Do not distribute out the bottom. I'm going to repeat, do not distribute out the bottom, because if you take a look, I have an x minus 4 on the top, I have an x minus 4 on the bottom, and we can cancel those to give me a 1 over square root of x plus 2. That's my extended function. So now to get this limit, I can now evaluate the limit as x approaches 4 of 1 over the square root of x plus 2. And if you plug 4 into that, the square root of 4 is 2 plus 2 gives me a 1 over 4. Okay, so again, multiplying by the conjugate, it's the same terms, opposite sign. Okay, as soon as you reduce it, then you can evaluate your limit. So again, you can see the terms that I have here. There are two problems. I'm going to write my answers up. You can pause it, you can check it, but ultimately I want you to do those on your own. So the answer I got for the first one was a 2 square root 2. And the answer I got for the second one was 1/4. So check your answers. Make sure that you get it. All right. And I'm going to go to the next solving type. So what I call the x plus h problems, right? We've actually done one of these already. And these just really require you to do a lot of distribution, combining like terms, and then we're going to simplify at the end. So if you take a look at this problem, it looks super, super complex. And actually a lot of wonderful things happen here. So what I'm going to do here is if I were to plug in 0, right? If I take and for space purposes, I'm going to just kind of directly substitute in 0 here. Those are the only two h's on top. I don't know why I started drawing a third line here. Then I'm going to take that and plug in 0 from the bottom. So what I have is I'm going to end up having a 4x squared minus 3x plus 2 minus 4x squared. Oh, you know what? Yeah, okay, I'm good. Plus 3x minus 2 all over 0, right? And if you notice, all of these terms cancel, and I'm left with 0 over 0, which is indeterminate, right? So that proves I need to do some simplifying. So what I'm going to do is I'm going to do just an enormous amount of distribution, right? I'm going to start, and I'm going to write this as 4x plus h, x plus h, minus 3, x plus h, plus 2, minus 4x squared, plus 3x plus 2. I'm sorry, that was a minus 2 at the end. There we go. All over h. Now, if you distribute all of this out, I'm going to have a 4, and when you multiply this, do all your double distribution, you get a x squared plus 2xh plus h squared. Distribute this next piece out, and now I have this huge list of terms all over h. Now I still have to distribute this 4 inside, but now you might start to see there are going to be a lot of things that cancel out here. All over h. And let's see, if we're neat and we keep track of stuff, 4x cancels with the 4x. The negative 3x cancels with the 3x. Oh, that should be squared. Sorry about that, guys. Sorry, that shouldn't be squared over here. Got a little overzealous with my squareds, so bear with me. And then last but not least, the 2 should cancel with the 2. So what I have is I have an 8x. A lot of writing here. 8xh plus 4h squared minus 3h all over h. Okay? Now, if you take an h out of the numerator, it cancels with the denominator, and I'm left with 8x plus 4h minus 3. So now if I want this limit, rather than evaluating that whole limit, I can just evaluate this one. Now, be careful because we have two variables here. The only variable going to 0 is h. So that's going to leave me actually with an expression, not a numerical value. This leaves me with an expression of 8x minus 3. So the name of the game here is distribute, combine like terms, be very neat and organized, okay? And then you should be able to factor out an h and cancel. And once you do that, you can evaluate your limit. And I'm going to write up my answers for, I believe there's 3 questions. So this one is, the part A is very similar to what we did, and I get an answer of 2x minus 5. And then this one is like the complex. It's a mix of complex and the x plus h problems. And for this one, if you do it all, I get a negative 1 over x squared. And then last but not least, if you do a conjugate with these radicals, so notice I'm trying to blend some ideas, I got a 1 over 2 square root x. Okay, so again, for the first one, I got 2x minus 5, negative 1 over x squared, and 1 over 2 square root of x. Okay, let's keep going. So limits that involve trig. Okay, I have now that this is kind of the big idea. This one is an important one that you need to know. Anytime you have sine of x over x, that's going to come up a lot. If you notice in red down here, anytime I have the same coefficient in front of x, so sine of x over x is always 1, and that's if x is approaching 0. Okay, so this is a big, big idea. Write it down. Okay, it's going to pop back up, but the limit as x goes to 0 of sine of x over x is 1, always. And more importantly, it's always just going to be the ratio of the coefficients in front of x. So in this problem, I have a over a, that gives me 8. Now, if your coefficients are different, that's fine. It doesn't make any difference. It's just going to be, that's going to be your answer, whatever the ratio of those coefficients are. So if you take a look at part A, ultimately, I have the sine of 2x over 5x. And the most important part, make sure it's going to 0. My answer here is just going to be 2/5. Okay. For part B, we have to do a little bit more working. Okay. But I can write this to be the limit as x approaches 0 of, I'm going to call this the sine of 4x over the cosine of 4x, because that's tangent, right? We get a little creative here. And then we're going to multiply by the reciprocal. So I get the limit as x approaches 0 of sine of 4x over the cosine of 4x times 1 over x. Now I'm going to rewrite this. Now pay attention to how I rewrite this. As x approaches 0, I'm going to take the sine of 4x and the x on the bottom, so these two pieces. So I just rearranged it, and that's perfectly legal to do. It's all multiplication, right? So I know that this first fraction is going to just be 4 based off of what we know. And if you do a direct substitution to the second piece, if you evaluate cosine at 0, that's going to be 1, right? So 1 over 1 is 1, and that gives me an answer of 4. Now, for the last problem, I do something very similar. I'm going to have the limit of sine of x over sine of x over cosine of x. I just rewrote my tangent. I'm going to go ahead and multiply by the reciprocal, right? So the reciprocal of the bottom. And this is as x goes to 0, by the way. So I have sine of x, and this would be cosine over sine. And these signs cancel, which now just gives me the limit as x goes to 0 of cosine of x, which is just 1. Okay, so that's how I evaluated limits with trig functions. All right, now there are 3 more to do. Okay, if you do these 3, again, they require a little bit of factoring, a little bit of canceling, but I'll share my answers. Actually, there's 4 here for you to do. For this one, I got 2. For the next one, I got 1. For the third one, I got 1. And for the last one, I got 1/5. Okay, so for A, I got 2, B, I got 1, C, I got 1, and D, I got 1/5. Now, piecewise functions is the next category. I think there's 2 categories left. So piecewise functions, we just have to know kind of how they operate. If you guys look at this, the first piece, the quadratic piece of the function is when x is greater than 2. So I have everything up to that point, including that point. And then the second piece is linear, is going to be that component. So if I want the limit as x approaches 2 from the left, this is ultimately just saying use the function that's on the left. So I can say that this is going to be this, I'm going to use the f of x, or 5x plus 2, because that's the left side of my problem. And if I do a direct substitution into that, I get 12. Now, if I do the right, I'm going to use the right side, which is actually going to be the quadratic. So that's the 3x squared minus 1. And if I plug 2 into that, I get 3 times 4 is 12. I get 11. Okay. And if I keep going, now I want to know at 2. So from the left and from the right, are those giving me the same values? In this case, no. So this does not exist. Even though the graph looks like it exists, but it's really the scale that's throwing you off. It's going by 50s, so you really can't tell. All right. Now, if I want to evaluate the limit for part D at 5, well, which side of my function is 5 on? What's on the blue side? So I want to use the blue part of my function. So I know as x approaches 5 of the 3x squared minus 1, if you plug 5 into that, I believe you're going to get 74. Okay. If I want to evaluate at -1, so which side is -1 going to be on? Well, that's going to be on the red side. So I'm going to use the 5x plus 2. So really, this all comes down to just figuring out which side you want to use, right? So if I plug in -1 using direct substitution, I get a -3. And if I plug in 0, well, 0 is also going to be on the red side. So if I take the limit as x approaches 0 of 5x plus 2, that's just going to give me 2. Okay, so for a piecewise function, you just have to figure out which piece of the function that you need to evaluate. Which side of the limit are you looking at? Okay. Now, there are a few questions here. I'm going to put up my answers to these questions so you can try to evaluate them. All right, one by one. Well, as you can see, all 3. The first one I got to be 9/4. Second one I got to be 4. Last one I got to be 10. Part D, I got to be 4. Part E, I got to be 5/2. Part F, I got to be 4. G does not exist. And H actually also does not exist. Okay, so these were my answers to these 8 questions. All right, last piece. Absolute value functions, right? So I have a common absolute value function here. The absolute value of x plus 2 over x plus 2. Now, do you notice how the numerator and denominators are the same, right? So you would think they cancel out, but that absolute value kind of affects things. So we want to talk about how to write absolute values as a piecewise. So we're going to kind of pair those two concepts together. So one, for part A, why is there a domain restriction at -2? Well, because as you approach -2, either way, you're going to end up getting something that's indeterminate. You're going to get 0 over 0. So I'm going to put that it's indeterminate at x equals -2. Okay? Now, we want to write a piecewise function for that value. So here's the best way to do it. I'm going to split up that function at -2, where I know it's indeterminate. Okay? Now, when I go to the left of it, I'm going to take that absolute value, and that's where I know it's going to be negative, all over x plus 2. And where I go to the right of it is going to be positive. Right? Now, you can reduce this function to be a -1, right? Because it's the same thing on top and bottom, but it's negative. And then x is less than -2, 1 when x is greater than 2, right? Because if you reduce this, that just gives you a 1. And now I have something that's a little bit easier. Now, take a look. Now, there's no scales on here, or the scale is difficult to read, but this is 1 and this is -1. You can see I have a constant function to the right of -2 at 1 and a constant function to the left of -2 at -1. So this is my piecewise. So now I can evaluate. Well, if I evaluate f of x at -2 from the left, that's a -1. -2 from the right is a +1. And at -2, that does not exist because the left and the right-hand sides are not the same. Okay? Now, I have 3 more here. Okay? I'm going to write my answers as well as the piecewise for them so you can kind of see how I'm doing it. So feel free to pause for part A. But this is my piecewise. So the negative version when x is less than -3, and the positive version when x is greater than 3. And ultimately, those cancel out to give you a -1/2 when x is less than -3, and a +1/2 when x is greater than -3. Right? So to answer this question, I got an answer of a -1/2. For part B, I had an x minus 4 squared over the negative version when x is less than 4, and an x minus 4 squared over x minus 4 when x is greater than 4. And if you reduce that, I get an x minus 4 over -1 and an x minus 4 over +1. X is greater than 4, x is less than 4. So now if I want to know from both sides, well, if I plug in from both sides in either case, from the left and from the right, when you do a direct substitution, I do get 0. And then for part C, my piecewise function is an x minus 1 over the negative version and x minus 1 over the positive version. Again, at that point where they divide, if you reduce that, I get a -1 and a positive 1. And if I want to know 1 from the right, I get an answer of 1 to be my answer. All right, so that takes you through all of the different types. I know this video was a little long. I appreciate you bearing with me, and let me know if you have any questions.